All right, welcome to our fourth class. So we have a little bit that we didn't get to cover in terms of review last class. We're going to continue with that and then move on to introduce new concepts. We started off with like introducing reliability function, right? That was the first thing that we learned as part of the reliability class. Today, we're going to go over hazard function. We are going to talk about sensor data. We're going to talk about the general framework for reliability for live data analysis or Weibull analysis. And you're going to get to revisit some of the material that, again, may look familiar to you with exponential distribution. Next week, we're going to dive deeper into live data analysis with Weibull distribution that I don't think most of you have seen, or log normal distribution. That's another distribution that's typically used for live data analysis. And we're going to continue with diving deeper into the reliability concepts. Okay, so let us start with our review. Conditional probability. We have, for instance, two events, A and B. Then we are saying that B has already happened, and now what's the probability of A? What did we say was the equation for that? Okay, just shout out. Exactly. Perfect. Thank you. And then we also talked about multiplicative law of probability, right? If I have, for instance, A and B being independent, what can I say about P of A intersection B? Maybe somebody else from that side of the class? Maybe shout out. Okay, continue. Probability of A, multiplicative, right? Times probability of B, exactly. Okay. So if I have more than two events, let's say I have events A1, A2, all the way through AN, then what can I say about their intersection? Intersection of AIs. It will be, again, multiplicative because they are independent, right? I can write this as P of A1 times P of A2 all the way to times P of, and like my screen doesn't allow me to write, times P of AN, right? You multiply all of them. And we can kind of extend this to other probabilities. Let's say the A and B are not necessarily independent. So let's say A and B not independent, right? We still have the chain rule, if you remember. We have A intersection B, we can write it as if like we can evaluate them in sequence, right? P of A, or like P of B times P of A given B, right? Or P of A times P of B given A. P of A times P of B given A, right? Right? Chain rule. We look at the first one, then what's the probability of the next one, given that the first one has happened, the probability of the third one, given that the first two has happened, probability of the fourth one, given that all of them, right? So we can go through it like one step at a time. Okay. Then we had law of total probability, right? We said that if we have a bunch of events, A1 through AN, right? Having two specific conditions, right? They are mutually exclusive and exhaustive, right? They are there's no overlap between them, and then if we get their union, they're gonna expand the entire state space, right? If we have these two conditions, and then we have a new event B, what can we say about P of B? We can write it when looking at only the intersections of B with all of these AIs, right? So we can write this as anybody wants to take a step? Remember this, right? A1, A2, A3, all the way to AN, right? I'm defining my new event B, the green one. I can write this as B intersection A1, B intersection A2, B intersection A3, right? And I can simply add them up because their AIs are mutually exclusive, right? So it will be the summation of P of AI intersection B, right? Or I can write as P of, again, using my chain rule, right? P of B given AI times P of AI. I can essentially rewrite B in terms of all of the AIs. Okay. And then we went on to learn or relearn Bayes' theorem. What was Bayes' theorem? If I have, let's say I have all of these P of B given AIs, but now I'm interested in the flipped version, right? I'm interested in P of, write this. I'm interested in P of AI given B. Sometimes we refer to this as posterior probability because it's as if I've had P of A, I, right? And now B has happened, so this will be prior, right? I have a prior P of AI, B has happened, now I'm interested in the posterior, like P of AI given B. So you may hear that from that perspective. Okay, so if I'm interested in P of AI given B, what can I write? Numerator will be P of AI intersection B, right? Denominator will be P of B. But with Bayes, we can essentially expand everything. So we are going to have P of B given AI times P of AI, right? Over P of B given, let's instead of a, I don't want to confuse you with AI is just an index. So that maybe I can write this as J, and this is numeration over all J's. P of a J. Right? Any questions? Good. Good. Right. And we also talked about counting techniques, right? Just one of them, I guess. We talked about n choose k. Anybody wants to take a stab again at the formula? Right. So n factorial, exactly, over k factorial, n minus k factorial. Okay. Right? Did I get it right? Yes. Right. Good so far. Okay. Then we switch gears, start talking about random variables. What is a random variable? It is essentially, and we said it's a function, right, that transforms the outcome to a value, right? An outcome of a random process to a value. We write it with, let's say, capital X or capital Y. We show it with capital letters. It gets an outcome. It produces value. Okay, so we said random variables can be of two types, right? They can be discrete or they can be continuous. Typically in this class, for the most part, for live data analysis, we focus on continuous random variables. But every now and then, I'm going to reintroduce some of the discrete random variables that you've seen before, because we're going to use them combined together for some of our examples. And you're going to see the application, for instance, in an exercise today. So discrete, when these x's, the values that the random variable can assume, right, are countable or finite sets, we say it's a discrete random variable. If the values that the random variable maps to is a point on a line, right, then we say it's continuous random variable. Can you give me an example of a discrete random variable? Perfect. Number of students present in class, right? What about continuous? What we are measuring or trying to measure for the most part in reliability engineering. Time to failure, right? Time to failure can be a random variable that maps to, right? That maps to its time. So it maps to a line, a point in a line, on a line, right? That's continuous. Okay, so then because we are working with continuous word, we introduce PDF, right? Probability density function. They said if we are interested for a continuous random variable, right? If you're interested, what is the probability that this random variable is between A and B, then we have a function, right? This is a function, fx. If we integrate that function from A to B, that would give me the probability of interest, right? If I have such a function, what are the criteria that this function needs to meet? We said there are two criteria that the probability density function needs to meet, right? What is the first one? What's the second? Greater or equal to 0. Okay, I take that. What am I writing the criteria for? Fx, right? So fx is greater or equal to 0. That's good. What's the second one? The total area, exactly. Under the, let's say, on the domain of x, whatever it is. Let's say from minus infinity to plus infinity. The total area under the curve equals to 1, right? There's no other condition, right? So there's no condition on the values that this function can assume. Remember, this is just a function, right? If we integrate this function, then we get probabilities. So the function itself doesn't give you probabilities. And we also talked about, for instance, in the continuous word, what is this probability? What is the probability that my product is going to fail exactly at time t? The probability is 0, right? In the continuous word, that probability is 0. I can always say, oh, what is the probability that it fails within this delta x, right? That is a valid question. You cannot give a probability to any single point. You can only treat delta x's or like an interval, right? Because you're integrating under a curve. Okay. Any questions? All right. Then we start talking about cumulative distribution function, right? We said that, all right, so I have a random variable, right? And I'm interested in a point in time. Let's say point in time, let's say call it t, right? So with lowercase values, I'm showing constant values, right? With capital letters, I'm showing random variables. So I'm interested in the probability that my random variable, capital T, is less than or equal to a little t, right? So if I have this line and this is t, right? I'm interested in, this is, let's say, my random variable, or the PDF, right? I'm interested in something like this happening, right? Time to failure be less than or equal to t, right? That is the PDF up to t, or sorry, that's a CDF at t. How can I find that? I integrate under the curve up to time t. Right? So this is then my random. So it says, what is the probability that my random variable, which is, let's say in our class for the most part, time to failure. This random variable time to failure, which can go from maybe 0 all the way to infinity, right? What is the probability that that random variable is less than or equal to t? Right? So you have to integrate the entire curve up to t, right? Under the curve up to t. So it will be, let's say, from minus infinity, or like the beginning of my domain, the values that my random variable can assume, right? All the way to t of fx dx. Fair enough? Okay. So then what is the reliability function? One minus, and by the way, we show this with capital F at time t, right? So if I'm interested in reliability at t, it's 1 minus f of t. It's complement of f of t. Because in essence, this is capturing unreliability up to t, right? The probability that my random variable happens up to t. So with reliability, I'm interested in what's the likelihood that it will last longer than t, right? So I'm interested in the right-hand side. What's the probability that it will last longer than t? Okay, question. We have, so sometimes we're going to get to it. So for life data analysis, typically most of the distributions that we're going to look at start at 0, right? But for instance, for some products, we may try to estimate their lifetime using normal distribution. And with normal distribution, we're going to get back to it. Normal can expand from minus infinity to plus infinity. But the likelihood that, for instance, if we think the mean is somewhere like around, like, I don't know, a large number, the likelihood that it will go to 0 or a negative number, it will be very small. So sometimes in this class, we're not going to work with truncated normal. But what you can do is to make sure that the lifetime is greater than 0, you can essentially eliminate these and put the probability, so scale this the rest of the distribution by 1 minus whatever you're not allowing to happen. So you're truncating and re-scaling. But so that's the only case, I think, that in this class that we allow the probability or the time to failure be negative. But it's so unlikely because of the way the distribution is organized for the most part, because mean time to failure is going to be longer or something. So it will be very small. So technically, we want the lifetime distribution to be great, or the time to failure to be greater and equal to 0. But we may relax that to just discuss normal distribution, because that is something that explains the lifetime in a lot of cases. Good question. All right. All right. Coming back to reliability function. How can I write the reliability function at t using my lowercase f? If I'm integrating, what am I integrating? T to infinity. All right, perfect. T into infinity of fx dx. Okay, excellent. And then, so we discussed that we can go from any of these 3 functions that we learned to the other one, right? So here, for instance, I'm integrating lowercase f, depending on where I'm integrating it. I'm going to either get capital F or capital R, right? So let's say I want to get lowercase f from capital F. What do I do? Take derivative. Okay. So if I want to get it from R, what happens then? How can I get it from capital R? Negative. Perfect. Okay, so I can go from each one. If I give you one, ask you about some information about the other one, you should be able to transition to the other one and give me whatever I want. Okay. Any questions? Good. Perfect. Okay, so design life. Let's see. Whenever we talk about reliability, right? For instance, we say, what is the reliability at time X, Y, and Z? Like, what is the reliability in hour 1? What is the reliability in 2 days? What is the reliability in 24 hours? What is the reliability, right? So typically, that's how we talk about reliability. And what do we mean by that? If I have this curve, if I have this T, right? What is the reliability then? And you look at this, you get the integral under this, and you say, oh, the reliability is R, right? But I can ask you this question from the upside down, right? I can tell you, oh, what is the longest I can run this motor if I want to have at least 90% reliability, right? I can ask this question from the other end, right? I can tell you, I'm interested in having 95% reliability, right? What is the longest time I can, I don't know, watch TV if I want to maintain I don't know, 99% reliability? Something like that. So what am I essentially asking? I'm giving you R, I'm asking for T, right? That is design life. If I'm giving you reliability, I'm asking for the time that makes that happen, the maximum time, that will be design life. Okay? So for instance, in this case, I'm giving you F. I am interested in the reliability of 0.9, right? Which of these 3 would give me the design life? Let's say it's in units of years. 3 years, 2 years, or 1 year? Just visually, if you want to pick one of the 3. 1 year, right? Because I'm saying, okay, I want the reliability to be 0.9. Accumulate all of these and tell me where I'm gonna have that. Right? So the T corresponding to that, TR or T, it will be T 0.9, right? So that's the longest that I can run my device or my motor or my whatever, right? And guarantee that I have 0.9 reliability, right? 90% reliability. It's not 90% reliability. No. So with the same attitude, we can define median with random variables, right? We had talked about median before when you had just a bunch of numbers. We said that median is like the middle point, right? When it comes to distributions, median essentially is, again, the middle point, but it's defined using probability. So median would be the point where I drew something very symmetric. So let's say median is the point where the area on both sides is 0.5. That's how we define median for random variables, right? It's about area. It's no longer about the number, right? Because now we have a curve and everything is defined based on probability, based on area under the curve. So if we typically show median with T med or mu tilde, right? So at that point, R of mu tilde is equal to F of mu tilde is equal to 0.5. So the area under the density curve to the left and to the right are equal, right? That's the point. That's what we call median for random variables, for a continuous random. All right, perfect. So I'll let you find the median. If you remember, we looked at this distribution before last class, right? We essentially found this number, right, to make sure that what we are looking at is actually a density function. Do you remember how we got it? We said we want f to be always greater than or equal to 0, and the total area under the curve to be equal to 1. So we estimated what that c should be, which we got 38 to be 38. Now I'm asking you to find the median for this random variable. Right, let me know if you have any questions. All right, a lot of you got it. Perfect. So you need to first pay attention when you are, I noticed a few of you did that. So when you're getting your fx, I noticed some of you tried to integrate this function, lowercase f, from 0 to 2. What do you get if you integrate your f over its domain? You're going to get 1, right? Because that's area under the curve. If you want to get your CDF or your capital Rx, right, your reliability function, you have to integrate up to a point, right? A point in between, like an x, a t, right? To get a function, right? Otherwise, you just get a constant. Okay, so let's do that. Let's integrate this. Do you prefer to find f or r? It doesn't matter. So I'm going to integrate this from 0 to x of, let's say, ft dt. So 3, 8, 4t minus 2t squared dt, right? So this will be 3, 8t 2t2 minus 2/3 of t to the 3, right? Evaluated from 0 to x. So it will be 3, 8, 2, x2 minus 2/3 of x3. I guess minus 0, right? Okay, so that's my fx, if I integrate it correctly, right? Okay, so we can quickly check. If I put my x equal to 0, I know fx at 0 should be 0. That sounds good. If I integrate my function up to the endpoint at 2, I should get 1, right? Let's see. Is f2 1? So 2 to the 2 times 2, 8. So it will be 3 minus, again, that will cancel. 3 minus 2 is equal to 1, right? So I quickly check. f0 is 0, f2 is 1. So I seem to have integrated correctly, right? Because at least I checked at 2 points. So that my overall fx will be 0 for x less than 0. It's this function for any point between 0 and 2, and 1 for any x greater than 2. Right? This is my overall function. Now I want median. So I'm going to set this function to be equal to 0.5 and solve for x. If I solve for x, a lot of you got it. You got 1. That's it. You could calculate f, you could calculate r, doesn't matter. Set equal, either 1 equal to 0.5, and you get the same 1 as the answer. So you can, let me take a second and show you how you could plot this to get your answer. So if you want to plot a function in R, right, you can either enumerate it, like let's say you can say that, okay, x is a sequence of numbers all the way, let's say from like -5 to 0.5 with a particular step size, and use the plot function to plot a scatter plot. But now we have a continuous function, so we can use the command curve. So I can use the command curve and say, okay, so plot for me 3/8 of 2 times x squared minus 2/3 of x to the 3, right? And I want to plot this minus 0.5, right? Let's say because then I can see that when it crosses 0, right? And that will be my answer. Does that make sense what I'm doing? Okay. So this is what I get when I plot it, right? Let's plot it when I have a little bit more control over this. So let's say xlim is from -1 to 2. Concatenate it, -1 to 2. So it plots a larger range for me, right? Okay. So I can add a line, AB line, there at 0, right? Horizontally 0. Okay. So, right, because this was my function that I wanted to solve, right? I wanted to find an x that makes this equal to 0. So I plot this, I plot y equal to 0. Wherever they cross between 0 and 2, that will be the answer, right? So I check between 0 and 2, they cross at 1. So that's my answer. If I want to get it, I don't know, if you find this to be easier. This was my way of showing you how you can plot things for the most part. You can use it to quickly get a visually inspect your function. You can do other things with it. All right. All right. Any questions about median? I could as easily, instead of asking you to give me the median, I could ask you to give me the design life at a given value, right? At a given, so you would just come at a given probability or reliability. Right? You would set your reliability function equal to that reliability value that I'm asking from you, and then calculate your x. So it's the same thing. Make sense? Any questions about the whole process? Okay. So we can calculate the mean time to failure using this function, right? We have seen MTTF or E of t before. So if I multiply t by ft and integrate all the way from -∞ to +∞, that gives me my expected value of the random variable. In lifetime analysis, we sometimes, or more often than not, we have t to be a positive random variable, right? It goes from 0 to infinity. So in those cases, we can use an alternative function or equation for finding expectation. So E of t will be equal to 0 to infinity of RT dt. This is the alternate function that you can use to calculate your expected value. Good. It's based on the reliability function. So sometimes if you have the reliability function, instead of taking the derivative to get your f and then using this function, this formula to calculate, you can directly calculate it using the reliability function. Make sense? Okay. So I'll let you practice. So find the MTTF using the first formula, right? Which was E of t is equal to, you integrate from -∞ to +∞, TFT. I'll let you quickly do this, and then we have another exercise for the other approach that I introduced. Listen, students, great to see that you're active and you're doing the exercises. Good job. All right, what did you get? Yes. Yes, you're still getting 1. So it's kind of like every answer with this question is 1, which is quite nice, right? I get to remember it, so that's good for me. Okay, so we are integrating from minus infinity to plus infinity, right? But look here, our function is positive only between 0 to 2. So we can ignore the rest, right? Because it's going to be 0. So it's equal to integrating from 0 to 2 of 3/8 4, okay, switch to t. 4t to the 2, let's highlight, t to the 2, right? Minus 2, again, t to the 3 dt. Right? And if you do the integration, you're going to get at some point 4 minus 3 equal to 1. So I'll leave that to you as an exercise. Question? Okay, so let's expand. That's a good question. All right. So what is this equal to? I can write this as from minus infinity to 0, tft dt, divided by minus dt here, right? Plus 0 to 2 of tft dt plus 2 to infinity of tft dt. Right? I can break it apart. What do I know about this one and this one? Let's say, what is my ft? From minus infinity to 0. 0. And here, same. Because my function is not positive, it's just, I can ignore them. Good question. Anything else? All right, so let's practice the second formula very quickly. So this time around, I'm giving you ft, but I'm also giving you rt. Take advantage of it, right? Use the second formula. Give me mttf first, and then give me median. You have rt, you can easily calculate median. That will be another exercise for median. The answer is not 1 this time, so calculate it. I'm confused. So like, I'll give an answer. I don't see those. Anybody got me? No one? What do you get? Shit. Expectation. I want E of X, E of T, or yeah. What do you get? I got something else. I got 500. So let's see. Let's see what happened. So we are integrating from 0 to infinity of e to the minus 0.002 t dt. Somebody asked me, what do we have RT or can we calculate RT? Let's refresh our memory. We can calculate RT, right? I'm giving you that because I'm feeling generous here, right? But in the exam, I may not feel that generous. So you should be able to calculate RT, right? So RT will be from t to infinity of fx dx, right? Or 1 minus ft, right? So you can calculate it, but here I'm just giving it to you to be able to do this shortcut formula, use this other equation. Okay, so this will be, so let's refresh your memory on how we integrated something like this. I have e to the minus at, right? I'm integrating that. What would that be? This, right? Excellent. Okay. So I have e to the minus 0.002 t over minus 0.002. And by the way, this was a good thing that somebody brought up. So if for some reason so your like computer crashes, or like your I don't know, calculator doesn't work for some reason, right? If you're stuck here, I can easily or like the TAs, like during exam, right? You can raise your hand, ask for the formula, right? If you don't, I mean, it's open book, but for some reason you don't know where the formula is, you don't have your book with you, we can allow you to continue. We can give you the formula, subtract some points, but let you continue. So if you have a situation like this, just raise your hand. We can come to you and like give you that kind of hint, right? Because technically you could have this like in your book, in your notes, but you don't have it. So I can provide that formula for you, because that's not the purpose of this class. The purpose is for you to be able to like get to your reliability, get to your like final values, like other things. So don't be shy to ask these kind of questions. If we can share something with you, we will. If we cannot, we will tell you that we cannot. So take advantage of it. Okay. So 0 to infinity. Okay. So if I'm evaluating the first at infinity, this is going to be 0, right? Because it's e to the minus infinity will be 1 over some, like e to the infinity or infinity, right? It will be 0 minus e to the minus 0.00, or actually I can just write this as 1 over, what did I miss? 0.002, right? And this will be 500 hours, because my units were hours. Okay. Anybody got the median? D46 was the median. All right, perfect. So how did you get the median? You said this equal to 0.5. Okay. So I have this to be equal to e to the minus 0.0002 t, right? And then you take the logarithm from both sides and then divide by this value, and you get your t net, which is equal to 346.6. Excellent. Any questions? Okay. Okay. We can also have mode. We don't necessarily use it very often, but I just wanted to make sure that you have it in your notes. If you have a function, it will be where the function is maximized, right? That will be node, because if I look at a delta t period, like a delta t units around that value, then it's gonna have the highest probability, right? If I'm looking at that this way. So for the function that we looked at, the function looks like this in last slide, last exercise. The function looks something like this. So the mode will be 0, right? Because that's where the function is maximized. So it's nothing fancy, right? Mode would be 0. Just where the function assumes its highest value. Okay. So we learned about MTTF, median, and mode. So let's just summarize it on one plot. Right? If I have a right-tailed, right, this is right-tailed or upper-tailed. And if I have a right-skewed function, so the mode will be somewhere, let's say around here, right? This will be mode. Then the median will be where the area on their both sides will be 0.5. Right? This will be the median. Like both sides will be equal to 0, so this will be mu tilde. And MTTF will be probably over here, so this will be MTTF or mean, right? For instance, in a right skewed function. So under what circumstance would these three fall on the same point? Well, normal distribution, which has a particular property, right? It's symmetric. So if it's symmetric, if I have a symmetric distribution, like normal distribution, right? It doesn't have to be normal. It can be a uniform distribution. Right? If it's symmetric distribution, so that's my only criteria. Both sides area under the curve is the same. Mean is gonna be in the middle. Everything is gonna happen like right in the middle on one. Okay, good. All right. So again, with the same thing that we learned with all the with numbers in the beginning, right? We said that mean, mode, median, they're all one number that are gonna try to summarize where my the center of the data is, or the center of the distribution is. They don't say much about the spread of the distribution, right? For that, we go to variance. So we have the same concept with distributions. We have variance of distributions, right? So variance of a distribution, we show it with sigma squared, right? For that random variable of interest, right? Or variance of x. And we can calculate it by x minus mu squared fx dx. Let's say from minus infinity to plus. Right? Or we can show it with p of x minus mu squared. Standard deviation is just the square root of this. And we also have a shortcut formula, which is variance of x is equal to e of x squared minus e of x squared, or mu squared. And obviously this mean, this mu, the same thing as Ex. I just showed it to you. Good? Okay. How do I explain it? So I don't want to like expand it. We can work through this equation to actually get to this equation. All right, so if you expand this, write this as P of x minus x2 plus mu2 minus x mu. Right? You can work your way to get the shortcut formula. But in essence, the shortcut formula is, this is essentially mu, right, squared. But this one is when you are integrating your function, right, it will be x squared fx dx. This will be this. Did I answer your question? Okay. This is actually a good exercise. Try to reach from this formula to this formula. Just for the sake of it. You should be able to easily get to that. So that's a good exercise. Okay. All right, conditional reliability. So we had talked about conditional probability. So it kind of seems like they are kind of related or similar. So let's talk about conditional reliability for a second. So let's say I have this function, right? This is my PDF. And I'm interested in the reliability. Let me ask a couple of questions first. Let's say this is my T0 and this is lowercase t units. Right? I'm interested in the reliability at time T0. How would you find that? Reliability at T0. I'm assuming nobody answers because everybody knows. Area under curve to the right of T0, right? That will be the reliability. So this will be the reliability at T0. What about reliability at T0 plus T? Simple, right? It will be this area, right? It means what? The random variable, capital T, let's say, right, fails after, for instance, T0. That will be when we can say that the random variable or the component who has this random variable as its lifetime is reliable up to T0, or is reliable up to T plus T, right? T0 plus T. So that will be reliability. Okay, so now I have a question. What if I'm not interested in all components? I'm only interested in those that have made it to T0. Right? Now I'm interested to know what is the likelihood that they will survive for another T period, given that they have survived up to T0. Right? When I say given that, you remember when we had Venn diagrams and when we say given that we only focus on like the event that we were interested in, we ignored everything in our sample space, right? We only drilled down on like this new event, this new sample space, and we looked at the proportion of, for instance, in that example, proportion of A to the new sample space. So it's kind of the same thing. I'm not interested in everything, right? I'm only interested in those components that are going to survive beyond T0. And I'm interested to learn what is the likelihood that out of those, some are going to survive longer than T0 plus T. Right? So that is called conditional reliability. So in essence, I'm interested in the probability that my random variable is greater than or equal to T0 plus T, given that my random variable is greater than or equal to T0. Right? Given that it has survived up to T0, what's the probability that it will survive for another lowercase t units of time? The way I show it is capital R of T given T0. So that's the shorthand. the probability that it will survive for another t periods of time, lowercase t period of time, given that it has survived beyond t0. Okay, with the Venn diagram, we saw that it will comes down to the proportion of B intersection A over the new sample space. So let's see what this will be. So I have P of, I can think of this as P of A given B, right? So this will be P of A intersection B, T greater than or equal to T0 plus T, and T greater than or equal to T0 over probability of B, right? Probability of T greater than or equal to T0. Fair enough? If I write in terms of two events, it will be A intersection B over P of B. Okay, so now let's look at the top events. One event is that time to failure is greater than or equal to T0 plus T. The other one is time to failure is only greater than or equal to T0. So what is their intersection? Think of it this way. I have a T0 and a T, right? One says T greater than or equal to T0. The other one says T greater than or equal to T plus T. Which one is smaller? Intersection needs to be smaller. It should be in both. Which one is in both? Exactly. So this essentially simplifies to T greater than or equal to T0 plus T over probability that T is greater than or equal to T0. So what is the top one? It's the reliability at T0 plus T over the reliability at T0. Now let's look back at our diagram or our plot. What is the numerator to the denominator? It's as if I'm looking at the proportion of where they both happen, right? Over, I'm slicing it. I'm scaling it for when it's greater or equal to T0. So it's kind of analogous to our Venn diagram, where we had A and B, and we said, oh, conditional on B. Okay, I'm going to slice B, throw everything out, and only look at A over B, right? A intersection B over B. So it's the same thing. So if I'm interested in probability that my time to failure is greater than or equal to T0, because I'm scaling everything to that. It's kind of analogous if you had that other image in your head. So this is the conditional reliability. So reliability, so let's read that again. Reliability function, or the probability that my component lasts for another t, lowercase t periods of time, given that it has already survived up to T0, is the reliability at T0 plus T over the reliability at T0. All right. So it's, yeah, I don't think you can read this, but it's useful when you have a warranty period or burn-in period. And we're going to look at exercises. Okay? Right now. Take a minute, go through this exercise, and raise your hand if you have any question. Yes, the first part is the homework, but the purpose is to get to the third part. from 0 all the way to variance 1. So in my case, it will be 0. Yeah, integration, yeah, of that, exactly. So ESP always works. Integration of RT only works in the non-available system here. If you go to negative, it doesn't work. So that's so with RT you're trading in steps essentially, as you said, but then it's like there it comes to value. You can only use it to part of that. Yeah, yeah, for the moment. Yeah. Is it? Okay. 4. Okay, that's it for RT. RT is 1 minus. But you are just at 2. So, where? Oh, that's that job. All right. Part A was the homework. So we calculate R of 1 over 12, which is 1 minus, I can write it. So what am I going to do is to calculate this to find my function, then put t equal to 1 over 12, because I want to use it in MTTF to calculate it. Okay, so I'm going to find a function. So integrate from t to 6 of u over 18 du, right? And this will give me 1 minus t squared over 36. So this is my reliability function. So I plug in 1 over 12, I get 1 minus 1 over 36 times 144. I get 0.9998, whatever. Okay, so that's what I get, part A. Part B, because I've already calculated my RT, I'm going to plug it in. And I know that t is positive, so I'm allowed to use the second method, right? So I'm going to integrate RT, which is this function, dt from 0 all the way to 6. And if I do that, I get 6 minus 6 thirds, and I get finally 4. If you prefer to use the first method, you can integrate from 0 to 6 of t ft dt, which is equivalent to 0 to 6 t squared over 18 dt, and this also gives you 4, so it doesn't matter. All right. The interesting part is the third part, right? This is a new part that we learned. So I want to know what is the likelihood that it will survive for a year, given that it has survived for a month, right? So I'm interested in reliability that given that, and always like try to follow the notation so that we can all look at the same thing and like just know that this is what everybody means. Given that it has lasted for a month, what is the probability that it will last for another 11 over 12 months or 11 months? So this will be equal to reliability of the summation, right? 1, 11, 12 plus 1 over 12 over reliability of 1 over 12. So that is a good thing about calculating the function, the reliability function, because you can plug in 112, you can plug in 1 instead of integrating the first part. But instead of integrating from 0 to 112, go for integrating from or whatever, like from x to infinity or 6. You use the functions. Actually, one thing, yeah, here. So this is what I'm trying to say. Calculate your function and then plug in the value. This would have been absolutely correct if you had integrated from like 1 over 12 all the way to 6 and calculate your 1 over 12, right? You would get a value. This is absolutely fine. But then it's more versatile. It's like more useful to calculate your function than plug in your values, because if I'm asking you for another value, you can just plug it into your function and get the value. So it will be, instead of integrating twice, which increases the chances of making a mistake or something, you're integrating only once. So this is just my suggestion, but it's up to you because both approaches are completely valid. Okay? So I'm going to plug in 1, and I already have the value for 112. So this will be 35 over 36 over, I have 5183 over 36 times 144. That's what I have, and then I get 0.9724. Is that what you got? Question. Okay, so the question again, it's just notation, but we are just trying to get on the same page with notation. This is how we write. We say how much longer, given that it has happened. So the question says, given that the refrigerator has survived its first month, what is the probability that it will survive the rest of the year? Right? But when we write it in our notation, we only write the remainder. Okay, I'll try to be very clear in terms of what I want. That's a good thing. But just again, to be clear, in terms of notation, so we write it this way. So T given capital T. So as long as we're clear on that, I'll try to make the wording crystal clear on like what I want from you. Okay, good. Any other questions? Okay. All right, perfect. So let's take 10 minutes and then come back here and reconvene and continue. That's not FFP. I have actually, I think I have the right actually. Okay. So let's look at RFP. Integral from P, which is V over 18 view. Okay?
Yeah.
Okay. That's the difference.
Okay.
But then I can explain that.
Oh, no, I get that.
You're integrating your function from that point to the right onward, right? So it's different. So if you draw, just maybe draw a distribution. And then let's mark it P. So you're interested in your time to failure to be some point greater than that. Right? So what you do, you integrate, it can be any point, right? So what you do, you integrate this function, evolve P, so shade everything, right? So that will be your RFP. The probability that your component will last longer than yours.
So on why is it this side?
Because
In a lot of cases, when this is bigger amount,
not always depends on bacterial speed, right? I can shift this to be this side being 1, I can push it all the way to here to this side.
Okay.
So that's just how we define reliability, right? Because you want what? You want to define reliability at time t that the likelihood that my component or the time to failure will be at some point after. That's the definition of reliability. So I want yeah, so it should stay at some point after that. So if I want, I'm asking, what is your reliability in day 1? 1 minus the probability that it has stayed by day 1. Right? So this part is the probability that has stayed. The time to failure has happened before T. This part is when the time to failure happens after T. Okay. So that will be the by definition. That would be the reliability at time T. Because the probability that your component will stay at or beyond.
so then we expected that 0 to 6 of that.
That is for entities, right? That's for expectation. Exactly. Yeah. All right, let's get back to it. Hazard function. Hazard function, as the name suggests, is a function, right? It measures the tendency to failure. So first things first, it's not a probability, it's a rate. It's the instantaneous failure rate, right? And it's rate, so it's calculated in a very small interval when delta t goes to 0. So it's a rate of failure in the immediate future. Okay, so we typically show it with h of t or lambda of t. Okay, so I want us to derive it together. So I'm going to walk you through a few questions, small questions, and then we're going to derive it together. So we want, remember, we want the instantaneous rate of failure. Okay, first let's start with the first question. So what is the probability that the system fails between t and t plus delta t using the reliability function? Right? Let's translate that. So let's say I have this function, right? And this is t. Let's say this is t plus delta t, right? What is the probability that the system fails in this period? That's easy, right? That will be the area under the curve here. But I want you to express it in terms of reliability function. Can you do that? With capital R. We have looked at it. You should be able to do that, right? Okay, so what would that be? One more time. Yes, exactly. Sure. Yeah, this is my PDF. Sorry, I just assumed that like when I draw a curve, everybody needs to assume that this is like PDF. But that's a safe assumption in this class. Just assume that if I draw something, it's PDF. Exactly, that's perfect. Right? Let's look at this. So reliability at t will be this, right? Area under the curve to the right of t. Reliability at t plus delta t will be area under the curve on the right of t plus delta t. So the subtraction of those two is going to give me the probability of failure between t and t plus delta t. Fair enough? Okay, so that's step one. Then I'm interested in the conditional probability of failure in t plus delta t, given that the system has survived up to t. So let's ask this first differently. If I was asking, what is the probability that it will be reliable after t plus delta t, given that it has survived up to t? Then this would be just conditional reliability, right? That would be reliability of t, or no, delta t given t, right? If I was asking for the conditional reliability instead of conditional probability of failure. So if I'm asking for conditional probability of failure, this will be 1 minus that. Does that make sense? So conditional probability of failure will be 1 minus conditional reliability, right? But then given that the system has survived up to t, in that period, it will be 1 minus. Okay? So let's write that this will be 1 minus reliability of delta t plus t over reliability of t, right? This will be RT minus R of t plus delta t. Maybe I should write it as t plus delta t over RT. So far, so good? Okay. So now, because I want the rate, I'm going to divide it by the units of time, which is here, delta t. So I'm going to get the same formula from the top, plus delta t over RT. And I'm going to divide it by delta t to get my rate, right, per unit of time. So that's it. I want the rate when delta t goes to 0. So I'm going to take the limit of this function where I send delta t to go to 0, and that will be my hazard. Right? It will be the rate of failure within the minuscule amount of time. right? Given that it has survived up to this point, starting from this point. So that's what I'm going to do. I'm going to take the limits of RT minus RT plus delta T over RT times delta T. Right? So I'm going to take 1 over RT out, take the limit, then, and like maybe a minus 2, T plus delta T minus RT over delta T. So what I did was I took a 1 minus, a minus 1 over RT out, and then I'm left with this equation under, over here. What is the equation that I've underlined in green? Derivative of RT, right? So this is 1 minus 1 over RT times dRT dt. That's it. This is my hazard function. I am going to show it with lambda t. So it's the instantaneous rate of failure at this point. And by at this point, I mean I've survived up to this point. So instantaneous rate of failure at this point. Right? So I can use my reliability function to calculate my hazard function. Okay, so again, I can use my reliability function to calculate my hazard function. Now I have a question. Can I calculate reliability function from the hazard function? If I give you reliability function, you can use this to give me back hazard function, right? If I give you hazard function, can you uniquely give me back a reliability function? So that's the question we want to answer now. So before, we've seen that we can go from lowercase f to capital case F to R and all the way back. So we could move from any of these functions to the other one, right? Here, I've shown that I can go from R to lambda. Now the question is, can I go from lambda to R? And if that's the case, if I can say yes to that, then I can move across all these 4 functions, right? If I can give you one, ask you for the other one. If you calculate one, you can move the other one. So it's very useful if I can show the other way also holds. Okay, so let's look at that. So first, let me rewrite this as dRT, dRT dt over RT. Okay, I have a question for you. Can you write this in a more simplified way? And I'm willing to give a question, to give a chocolate for that. Yes, but that's not my answer. But that you're right. So I can write this as f of t, the total, over RT. So that's good. Thanks for bringing that up. Right? So this is absolutely correct. Right? This is ft over RT. Okay. So what I want you to look at is you're taking the derivative of a function in the numerator, and the function is in the denominator. Derivative of what else? It has. Oh, sure? I don't want to hit you in the face. All right. There we go. That's it. So derivative of natural log, right? So I can write this as ELN of RT dt. And this is equal to lambda t, right? If I reorganize this, I'm going to get lambda t, and I have a minus by that. Minus lambda t is equal to, or d times dt, is equal to d ln RT. Right? Great. So let's take integral from both sides. Right? I'm going to integrate from 0 to x. Right? Okay, so on the left-hand side, I'm going to have integral from 0 to x of minus lambda t dt. On the right-hand side, if I take the integrate is going to cancel with d. I'm evaluating at 0 and x, right? So the right-hand side will be ln of Rx minus ln of R0. Are you with me? R0. What is reliability at time 0? 1. What is ln of 1? There we go. So this whole thing cancels. So I have ln of Rx equal to something. What did I set out to do? I want to get my Rx. So if I exponentiate both sides, I got what I wanted. So Rx, so let me find the place to write it. Rx will be e to the minus integral from 0 to x of lambda t dt. That's it. This is the ultimate function we wanted. So now if I give you lambda t, you can give me RT. So we can go from any of these four, RT, capital FT, lowercase ft, lambda t, to any of the other four. So remaining three. Good. Okay. So I don't expect you to be able to go through all of these equations or derivatives or whatever. What I want you to be able to do is to use the equations that I circle or like put a box around, right, and calculate things. Okay. So let's practice. There we go. I'm giving you the hazard function. I'm asking you a design life for a given reliability. Let's practice. You want to find R from lambda and then solve it for R equal to 0.98 to calculate your time design life. So this is your lambda. So today we typically design life, we want all, we want the lambda function. So usually the equation gives you last life, if you write it down, so the equation is RT is equal to e to the minus, and then you have from 0 to t, lambda u, 0 to t of lambda u, u. So that's because you're then function. And then so the RT is equal to this amount, from 0 to t, 0 So a lot of you got it. So let's quickly look at it. So first, we say, oh, the question wants something to do with reliability. So we need to calculate the reliability function. Step 1. Reliability function RT is equal to e to the minus 0 to t of lambda u d. Right? So it will be exponentiating minus, and if I integrate, let me skip a step. So I'm going to do minus 5 over 2 times 10 to the minus 6 t squared. Right? I integrated everything. And now, what do I want? I want the design life. Right? So I want to set this equal to 0.98 so that I find the t corresponding to that. That makes that happen. Okay, so if I find the design life at for reliability at 0.98, this would be square root of logarithm of 0.98 over minus 2.5 times 10 to the minus 6. And that will be 89.9, which is almost 90. What is my unit? Amps. That's it. Good. Any questions? So no problem moving from lambda to R to lambda, F to R, F to capital, lowercase f to capital F to lowercase f. So you got to practice those four, moving from each one to the other. Okay. So hazard function is very important, as you might have guessed, in reliability engineering, right? And it's so important that even for the simplest thing of a function being increasing or decreasing, we have particular terminology. We have IFR, increasing failure rate, when our function is increasing. We have constant failure rate, or we call it constant failure rate when the function is constant. And we call it DFR when the function is decreasing. So with the shape of the function, whether it's increasing, decreasing, or constant, we call it IFR, CFR, or DFR. Okay. That brings us to the bathtub curve, which is one of the most important hazard functions for products that's commonly used. It's called bathtub curve because of the way it looks like a bathtub, right? And it consists of three parts. So the first part, zone 1, it's called burn-in or infant mortality zone. What do you notice about the hazard function from T0 to T1? The hazard function decreases. So it's decreasing failure rate. Right? Then in zone 2, we have useful life zone. What do you notice about the hazard function? It's constant. In zone 3, we have wear out zone. What do you notice about that? It's increasing failure rate. So let's think about the third zone, increasing failure rate. Why do you think failure rate may increase? When did that happen, by the way? Towards the end of the lifetime, right? Wear out, right? When it starts to wear out, it starts to fail, maybe at a higher rate or more frequently or things like that. During the most of the useful life, we have the system can only fail because of stress-related failures. Okay, so these are all meaningful. What about the beginning? Why do you think something can have a decreasing hazard rate? That is typically related to quality flaws, right? Let's give an example. Let's say you buy something from IKEA. Anybody has shopped from IKEA before? Okay. How was your experience? Pretty good? Okay, you're an engineer. So let's say you buy something from IKEA and like it comes in a package, you have to assemble it, like you end up probably like having an extra pin or like multiple screws, you don't know where they go, right? And then you put together a shelf, right? In the beginning, I'm sure you're scared of like putting any weight on it, right? It may fall apart. So why? Because it may not have had the craftsmanship or has the like very high quality, right? Because okay, I put it together, right? But then once you have that confidence, so that the failure rate is kind of high, right, in the beginning. But at some point you're like, oh no, this looks good, this looks stable enough, right? So you start using it, right? Putting books on it, removing books. If somebody knocks it over, it may fall apart, but that may be accident related, right? It's not necessarily because the weight of the books are like crushing the shelf or anything. But over time, things may like start to get loose, things may start to fall apart, right? That is wear out, that's kicking in, like maybe like in 2 years, 3 years, 5 years time window. So this is just one example of like how, for instance, one item that you may interact with work. So now think about like an area of items that is produced by a manufacturer. Like let's say we produce 1,000 items, right? So in the beginning, if you start like testing some of them may have quality flaws. During the process, they may not have like I don't know, gone through some of the screws may be loose, some other problem may be happening with it. But then at some point, if you go through this lifetime, if you start testing them, some of them may start to fail. right? Let's say in the first hour, like some of them start to fail. What happens with the ones that pass through this 1 hour of test? These are the ones that have survived that. So these are the ones that are going to have good life, right? So you're past that quality related issue. So those are failed. Now, among the ones that have survived this burn-in period, right? These are going to be like quite stable lifetime until they go through this their useful lifetime and they start to wear out. So that's the other way of thinking of it. Think of it as scale. So typically DFR is reduced by burn-in period, screening, quality control, acceptance testing. During useful life, you can use redundancy or excess strength to make sure that your reliability is as high as possible. And then when you increase to the end of life, when you have an increasing failure rate, you can reduce the amount of pressure or stress that you're putting on your component by derating or maintaining it, right? Or replacing the parts. So these are the strategies used at different stages of the lifetime of a component. Okay. So now I have a question for you. And hopefully by going through this burn-in or the infant mortality zone or the beginning where you have a decreasing failure rate, it's going to be more meaningful. So let's check first. Let's look at this hazard function. So is it IFR, CFR, or DFR? Is this function, or in other words, is this function increasing, constant, or decreasing? Increasing? Decreasing, right? If your t increases, your entire function decreases, right? So you have DFR. Okay, now with the knowledge of DFR, let's answer part A and part B, and then we're going to come back and conclude. What does that mean to get those numbers? Mm, do it one time. One person is something that and figure out what to put a and what I'm not. And then what to do with what we thinking of here. Because I want to the function of the so that we can mark that. And then you want to be very nice starting from one. So you want to find the key, not the second part. And you know the opposite of Is it? Okay.
Is it allowed?
Million years? I don't think so.
Well,
Well, it's million year off, but it's 11 cycles, so it's not divided by a million.
hey,
I don't know.
I'll take
I
that.
think I guess 11 years, not 11 years. That's a good time buying that
That's
product.
what I'm saying.
Yeah, I know.
I'm gonna put a price tag on it. Okay, it's going to be.
But that's the downside is nobody's gonna come back to you and buy another product because you're fine for 11 years. So you're going out of business.
I'm thinking I'm a lot of money.
Yeah.
I'm like, I'll offer updates. I'll offer updates.
You have good? I don't think so. Thank you so much. Save the day. Okay, so I'm gonna go back and repeat. So essentially, calculations, you don't need to hear my voice for that. But here, so we were saying, so essentially, if you have a new product, right, according to this decreasing failure rate hazard function, right, if you are interested to assure that you have 90% reliability, you can run it for 11.51 years, right? And you're sure that you have 90% reliability. But then you let this component run for 6 months, right? Or like 1,000 of them to run for 6 months. You look at those that survived the first 6 months. Now, if you like imagining that this is the product now, like that you ship out, right? So if you want to have 90% reliability, now you can let this component run for 15.8 years. So you get almost 4 years extra for making sure that it runs the first 6 months. And that's because you have a decreasing failure rate. Right? So this is one way of getting over this hump. So if you essentially do testing in house, right, and only ship the ones that survive this burning periods, survive this testing, then you can assure that you have longer useful life among the ones that essentially survive this testing, right? But the good thing is your customer is not going to have a lot of failure on their hand early on in the life cycle of the product. Does that kind of make sense? It's very counterintuitive, but at the same time, they showed it. And you can calculate, so the whole thing got messed up. Oh, I'm sorry. The whole thing got messed up. But anyway, any questions? What? Yeah, you can plot this. You're going to see that it is decreasing. So whenever you have a decreasing hazard, you're going to have this property. The longer you're burning, the longer the probability that it will survive. So the thing is, because your hazard starts kind of high, things are going to fade quickly in the beginning. But those that survive are going to present a longer lifetime. Okay. All right. So let's start talking about life data analysis, because that's essentially what we ultimately want to do as one major component of this class. We want to be able to understand from a sample what a population is gonna, what is the quality, what is the behavior of the population of products. Right? So we are gonna, this is typically referred to as life data analysis, but because Weibull distribution is a popular, very prominent distribution that is used in these kind of life data analysis, it's sometimes referred to as Weibull analysis, right? And the essence is we have a sample, we want to understand something and pass a judgment about the population. So I produce a bunch of products. I want to look at maybe like a few of these, right? Do some kind of testing, understand their behavior, how long they're going to last, what is the mean time to failure, and so on, and then kind of project that to the entire population to pass a judgment about the entire population. So sample versus population, we had looked at this. Sample is smaller, but then population is the entire thing. And the quality of these samples that you're getting is going to impact the quality of the judgment that you're passing. The more samples you have, the more accurate are your estimations. Okay, so there are 4 steps into performing life data analysis. You start with collecting data, like obviously, right? And then you select the life distribution, fit the best data, fit the best distribution you can to your data, and then estimate the parameters, and then use the parameters in your distribution to kind of calculate all of the components, all of the properties that you want about your population. Either it's mean time to failure, it's a variance, it's a reliability function, hazard function, whatnot. You can do all of that. So a little bit of repetitive stuff, but these are the kind of the terminology you may hear about. Attribute data versus variable data. We know of them as discrete data versus continuous, right? So this one is answering how many, how often, what kind. The other one is answering data, how long, what value, or how much. Okay, so let's start by like looking very quickly at what kind of data you can collect, right? We are gonna only briefly this class talk about the data and censoring. From next class, we're gonna assume that whatever data that we see is true state of the world, we have full information. But this is something that you may come across, so I wanted to just mention it very briefly. So complete data is when you have all the information you want when you're collecting your data. So let's say I have, this is time, and I have sample 1, sample 2, and so on. So remember, we are interested in time to failure. Let's say I start my first component to run, and I run it until it fails. I start my second component to run, like let's say I'm testing, right, until it fails. The third component to run until it fails, right? Now I have complete data. I know exactly how long it takes for them to fail, for the motor, for a washer, for anything, right? Okay. But we are not always that lucky. We don't always have that complete information. Sometimes we have incomplete data. What does that mean? We can have single sensor data or multiple sensor data. This is typically coming from testing, and this is typically coming from field studies or field tests. So this is when everything has the same time frame. From start to end, you have the same time frame for your testing. With the field data, you may change a washer right now, and then something fails. So while you're at it, you may change something else, some other components too. So you are removing things before the failure has already occurred. So you have incomplete data. But let's dig deeper into sensor data or singly sensor data. So what do I mean by raw sensor data? So let's go back to our experiment. I have sample 1, sample 2, sample 3. Let's say I start testing, right? And I've said that I want to test things. I have to make a report. I have to like report to my boss in 24 hours, right? So I start testing. First component fails here. Second component maybe even fails earlier, right? And then I get to 24 hours. My test is over, but my component hasn't failed yet. Okay. So there are two ways I can handle this, right? I can either throw this sample data away or out because it hasn't failed yet, right? So I don't know the exact time to fail yet. Or I can partially include in my calculations or in my inference that one of these components lasted longer than 24 hours. So it will fail at some point, maybe here, here, here. I don't know that, but I know it at least lasted 24 hours. So this is called right sensor data. Because I don't know the exact time to failure, I know that it will fail some point after 24. Sometimes I have left sensor data, right? I start my test, sample 1, sample 2. I have the same 24 hours, but this time around, I'm not monitoring continuously. I start my test, maybe leave, and come back in 24 hours, right? I see that this one is working, but this one is failed at some point, right? So I don't know the exact time of failure. I just know it happened at some point before 24. So this is referred to as left sensor data. And you can have also interval sensor data. So this time around, I have maybe checking on my system every hour or every few hours, right? So let's say I have sample 1, sample 2. Right? So this one, I check it up to here, it was working, and up to here, it was working, and up to here, when I check, it was failed. So I know that it failed sometime between these two. And maybe this other one, when I check, it failed sometime between these 2 points. Right? So it's interval sensor data. How are these even relevant to us? So let's look at that. So we have 10 samples here, and I'm reporting the time to failure for each of these samples. So the first one fails in 100 hours, the second one fails in 75 hours, 122 hours, and so on. And they're maybe failing for different reasons. Maybe the first one is failing because of overheating. The next one is failing because of battery leak, right? The third one is failing because of loss of contact. Okay. So my objective is to analyze the time to failure, regardless of the failure modes. I know you guys are getting tired. I'm going to try to let you go quickly. Okay, so we are analyzing the time to failure regardless of the failure modes, right? So I'm going to try to mark this on my plot. So sample 1 fails at 100. Sample 2 fails at 75. Make sense? So you have this. Now I'm asking a different question. So I want you to analyze the time to failure for specific failure modes. For failure mode type A. Let's look at that. Sample 1 fails at 100. What do I know about sample 2? Okay, but what is my question of interest? I'm only interested in type A, right? Mode A. So it is right censored. Why is it right censored? Because I know that it will fail. It would have failed by A at some point after this point, right? So it's right censored. So instead of just throwing it away and not include it as part of my estimation, I could include a condition on the fact that it would have failed at some point after. Maybe that gives me some partial information. Right? In this class, for the most part, we are going to deal with full information, not partial information. But in the field, if you start working as reliability engineers, you may get actually partial information, and you may want to take advantage of it in some way. And a lot of those are used in non-parametric statistics or non-parametric models. In this class, we mostly cover parametric models. Okay. So that's all I wanted to say about sensor data. So I know it was very quick. I just wanted to give you the terminology. So at least if you hear it, you know where to start, how to deal with it. So I'm not going to go into a lot of details about live data analysis, but let me just talk about the introduction a little bit. So we had talked about lowercase f, capital F, RT, and lambda t. What we want to do next is to analyze these 4 functions for a series of lifetime distributions: exponential, Weibull, normal, and log normal. They're commonly used to capture the time to failure of components. Right? And they are called parametric models because they have a fixed number of parameters. These parameters for life data or life distributions are typically of 3 types: location, scale, or shape. Let's very quickly look at them. Location parameter. As the name suggests, it changes the location of the distribution. So if I have a distribution like this, if I change the location parameter, maybe my distribution moves to the right or to the left. So it changes the location. Then I can have the scale parameter. The scale changes the spread, right? So if I change my scale parameter, maybe my distribution goes from this to this, right? Just the scale, just the variance or spread of it changes. So it goes from this to this. And then shape parameter. Whatever is not location or scale is typically shape parameter. So you're going to look at a family of distributions. There you can have a distribution looking like this or looking like this, dependent on the shape parameter. So it changes the shape of the distribution. Okay. All right. So next class, we can wrap it up today. So next class, I'm going to start reviewing very quickly binomial distribution, then jump into the 4 distributions that are introduced: exponential, Weibull, normal, and log normal. All right. Thank you so much, and I see you next week.